future you will thank you. All right, so similar triangles today. So now we are specifically talking about triangles, not just any old shapes, okay? So if you remember triangles, let me make a little shape here. So remember the example we just did with those hexagons, and I had two hexagons that all had the same length, but one of them I was able to just like knock one side of it in. So that kind of makes that shape a little too wiggly, right? But if you take a look at a triangle, triangles are known as rigid shapes, right? Let's see if I can put it on here. Because if I push on any of the vertices, it's not going to go anywhere. This side doesn't just cave in. Right? If you have a four-sided figure, let me just show you that real quick. So this is rigid, it's not going anywhere, but if I turn this into a four-sided figure, look what happens. Things start getting wiggly. If I push on a vertex, oh my gosh, this would not be a good idea to use a shape like this in a building structure, right? Because if I put pressure in certain points, now I got a problem. But that's a great reason why you see triangles so much in bridges, building designs, triangles, because they're so strong. Push on it in any vertex is that, well, I mean, I just almost broke the plastic, but they don't just squish like the other shapes do. I'm sorry. Okay, so any hoosers. So we have triangles being rigid structures. And let's see. So, do you recall the third angle theorem? If two angles in one triangle are congruent to two angles in another, doesn't their third angle automatically have to be the same? Remember that? Because they all have to add up to be 180. Okay. So, these are our three sort of shortcut ways to prove that two triangles are similar. Now, notice this is a big difference between similar and congruent. When we had our 5 ways to prove triangles were congruent, side, 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 angle, 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 side, hypotenuse, leg, right? We were proving things were congruent. In that list of 5, there was no angle, angle, angle. However, you can use angle, angle for similarity. And I don't have to do all 3 because of the third angle theorem. If 2 angles are the same, the third one automatically is. So we just call it the angle, angle similarity postulate. So here's what it says. If 2 angles of one triangle are congruent to 2 angles of another, then our triangles are similar. Not congruent, but they are similar. Okay, so that's all I would have to test. So if you remember yesterday, or maybe even the day before, if I wanted to show that 2 things were similar, I'd have to test 2 things. All the angles being the same and all the sides being proportional. With triangles, we get to shortcut that. I can just check if 2 angles are the same. That's it. That's kind of nice. Another shortcut that we have, imagine that we don't know anything about the angles, but I do know stuff about the sides. What I can do is I can compare all of the corresponding sides. If all pairs of corresponding sides are proportional, then the triangles are similar. And I want to stress all. You can't just compare 2 sides and 2 sides. You have to check all 3 with all 3 and make sure that they have a consistent scale factor throughout all of the ratios. Okay, and then the last one is side angle side similarity theorem. Let's see what this one says. 2 pairs of corresponding sides are proportional. And the included angles are congruent, then the triangles are similar. And you guys know the answer to this last blank. If two triangles are similar, the corresponding sides are proportional. Okay, so let me show you an act. Yeah.
What was the one for that because triangles are rigid structures in the third?
Oh, that's just because of that, you can say these things.
Oh.
Yeah. So basically, because you have angle, 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 you can say angle, angle. Yeah. Okay, so I do have a real world use for this stuff, which is kind of cool. So let me set the scene for you. In fact, I will draw you a picture. Here's the ground. Here is, oh, let's pretend it's the tree at Rockefeller Center, which I think is being lit tonight. Did you know? Here's another fun fact. I think it was 2017, I want to say. The tree that they cut down and put in Rockefeller Center was from my hometown. It was very exciting. My mom went and she like watched them. It was like a whole production to take it down. You see them put it up in New York. Have you seen like it always looks so bad when they put the tree up at first. Because you know, it's traveled a long way. The branches are broken. It's sad. It looks a little worn.
Do you want us to draw that too?
Yes. Draw yourself a beautiful tree. And I want you to imagine, here you are, a spectator, you're admiring this beautiful tree. There's you. Let's say you were there. I mean, I would be amazed if anybody actually did this because you never would, but you could do this. If you were like, gosh, I wonder how tall that tree is. Now, I know you would just say, hey Siri, how tall is the Rockefeller Center tree? And she would tell you, but pretend we don't have her. Let's say you are trying to find the height of this tree or anything that's too tall. You don't have a ladder. You're not, what are you gonna do? You gotta take measure that long? Of course not. But here's what you could do. You know how tall you are, or you could have someone measure how tall you are. And you could also measure the length of your shadow on the ground. So let's just say for easy numbers, how tall do you want to be? 5 feet or 6 feet? Let's go 6 feet. I'm so short. I've never been 6 feet tall. I'm going to pretend. Let's say you are 6 feet tall. You can easily have someone measure your shadow, right? If you're standing there, they can measure the length of your shadow. How long do you want the shadow to be? Could be anything. 9? Okay. Let's say your shadow is 9 feet long. Couldn't you, at the same time of day, measure the length of the tree shadow on the ground? It is, but, well, so the tree is going to have a shadow, right? How long do you want the tree? I'm making these numbers up, so I have no idea. How long do you want the tree shadow to be?
54.
54? Okay, fine. Let's say the tree shadow is 54. You could measure that along the ground, right? I would love to see you in New York City with a tape measure measuring the shadow on the ground, but you could, it's feasible, right? You could actually do it if you wanted. I don't know, buildings get in the way, so let's just assume that the situation is right. I want to figure out how tall this darn tree is. So I'm going to be looking for this length, right? I can use the fact that I have basically created two similar triangles to assist me. Now, hold on a minute. Hold the phone. Do you see the triangles I'm talking about, first of all? So I can imagine just drawing a third side from the top of this to the top of the shadow. Same thing over here. So I have these two triangles. I'm claiming that those two triangles really are similar in real life. What'd you say? You're right, but pretend we didn't know that yet. Pretend I just have these two triangles. How do I know that they're similar? Because now hold on. You can't set up a proportion saying x over 54 is equal to 6/9 unless the triangles are similar. So you better be able to show me that one of these three things is true. You better have angle-angle similarity, side-side-side, or side-angle-side. Now, you can't do side-side-side because you don't know the length of all three sides. So that one's out. Side-angle side, I claim you can't do that one either because you don't know how tall the tree is. You would have to know the lengths of two sides and check if they're proportional and see that the angle in between them is congruent. So I can't do that. So I'm leaning on this angle-angle. I claim that you know for a fact that two of the angles in this triangle are the same as two of the angles over here. How? Why? Give me one that you know for sure, hopefully. Which angle has to be the same? The 90-degree angle, right? The tree is going to be perpendicular to the ground and you're standing perpendicular to the ground, right? Okay, so I think we can all agree that we're going to have a 90-degree angle there. So cool, there's one angle. You would need a second angle. Not all right triangles are similar to each other. But here's a claim that I'm going to make. I claim that these two angles right here, that one and that one, really are the same. Do you know how I know? But you would have to know that these lines are parallel. Do you know that? You do. What creates a shadow? And what's going on with the rays of the sun as they enter our atmosphere? They're parallel to each other. First of all, that's wild. The rays of the sun are parallel as they enter our atmosphere. You see, I do have a little science in me. So anyway, these two really are going to be parallel to each other. Don't you remember like those images in like your science textbook and they'll show you like all the light and it comes in and bounces off? Haven't you seen images like this where all the sunlight comes in and does that? And then once it hits things, sure, it scatters. But as it's coming in, as it's streaming in through our atmosphere, it's parallel. That's so wild. So these two triangles really, truly are similar to each other. So now, yeah, I can absolutely solve for the height of this tree by setting up a proportion x over 54. If I do that, what do I have to do on the other side? If I do x over 54 over here, I'd have to do 6/9 cross multiply. I mean, I know you already know the answer. It is 36. I don't know what 6 times 54 is. 324. Yeah, I know you don't even have to go through all of this, but anyway. You can do this in real life. You can do this. You want to find the height of a flagpole? You want to find the height of, anything that basically you can reasonably measure the length of its shadow. Now, conditions do kind of have to be right. You need to have a flat surface, right? So if you're trying to measure something and it's not a flat surface that you're trying to, things are going to get a little messed up there a bit, but how cool. You really can do that. The other thing is I made the point that this has to be at the same time of day, right? Because the length of your shadow would change. So you would want to measure length of your shadow and the tree shadow at, pretty much the same time. Wow. I wish we could take a field trip to New York City.
Yeah.
I'd be so excited. I haven't been in a long time. I just think, what is stopping us? Well,
Nothing.
a worldwide pandemic, but besides that.
No.
All right, any Hoosers. So there is that. And oh gosh. Let me do this. Let me just show you what 7-6 is about. There is a chance that I won't be here tomorrow. So what I would like to propose, let me do 7-6, and then tomorrow, whether I'm here or not, we can do our work for these in class tomorrow, whether I'm here or not, because I'm pretty much, this is the end of the chapter, right?
Tonight?
Yes,
Okay,
right.
that's good.
Okay, So, and 7-6 isn't very, it isn't too long. So let me just get the notes out. So then that way at least we have them. So then if I'm here tomorrow or not here tomorrow, it doesn't matter. Okay. Sorry. And then I will let you go on a walk after this if you want to. But any hoosers. Side splitter. Do you remember I mentioned that to you the other day? Side splitter. So let's see what this is all about. This says, if a line is parallel to a side of a triangle and it intersects the other two sides, then the line, you ready for this? It's going to divide the sides. And I'm going to underline sides because it's the sides only. Divide the sides proportionally. So you did a little bit with this in your homework already. They just didn't refer to it as the side splitter theorem. So let me explain what's going on here. You have a triangle. Any old triangle, doesn't really matter. You're going to draw a line parallel to one of the three sides of the triangle. It doesn't matter where it is. So I'm just going to draw a line that's parallel to the bottom of my triangle. So, and I'm going to draw it kind of low. I'm going to draw it way down here. So here's what I need to know. I need to know that those two are parallel to each other. Here's what side splitter is telling us. It's telling us that the sides of the triangle, the two that are getting intersected by that line, are split proportionally. So if this was X, this was Y, this was Z, this was W, I could now claim this. X over Y equals Z over W. We can't normally do this because Y is not a whole side of the triangle, right? It's just this weird little piece. So normally, I can't say the whole side of a triangle is equal to a tiny little piece, but with side splitter, it works out. Okay, as long as I do the same thing on both sides. So X over Y can be the same thing as Z over W. Now, again, you can write this proportion any of the other ways that's the same. So if we took the reciprocal of both sides, yada, 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 that's fine. Now, I want to show you how I use this in a festive way. Lots of festivities in this end of chapter 7. Oh my gosh, look how dark. Let's try that. Okay, there we go. So let me give you a problem where we're actually trying to use this, and I'll show you what I mean. So let's say I have some other triangle over here, and let's say this time the parallel line is here. So these two sides are parallel. And let's pretend, I don't know, I'm just going to throw in some numbers. Maybe that's 4. Maybe I don't know what that is. Maybe that's 5, and maybe this is 7. So if I were going to ask you to solve for X, I'm going to show you what I do. You don't have to do what I do, but you're welcome to it if you want. You ready? I take all of my triangles with this third parallel line and I turn them into a Christmas tree. Want to know how? I pretend that that parallel line is a piece of garland, and I always want the garland and the base to be horizontal. So I literally turn my paper around, or I imagine it in my head. So I have my garland, and here's the base of my tree. I draw the trunk of my Christmas tree right there, and then I put the star at the top. So when I go to set up my proportion, I literally do this. I start at the star and I work my way down. Start at the star and I work my way down. So my proportion would be 4 over X equals 5 over 7. Start at the star, work your way down. You don't have to do it this way. But I will say, I've been doing it many decades now, and it's never steered me wrong. And now I just saw my proportion. Boom, boom, boom. Even if you don't celebrate Christmas, that's fine. It could be any holiday. Just draw yourself a trunk and then put a, you know what? I actually don't even have a star on top of my tree this year. I have a snowflake and it projects onto the ceiling. Isn't that neat? I never saw that before. Unfortunately, my tree is kind of close to the ceiling, so it doesn't have this big grand like projection like I was hoping that I saw in the ad, but that's okay. Still is lovely. So you can pretend it's a whatever, a snowflake, a whatever. Okay, so just start at the top and then you work your way down. There is a proportion that will work every single time. So if I do that math real quick, 28 is 5x divided both sides by 5. 28 divided by 5 is 5.6. So that missing piece right there is going to have a length of 5.6. So I know I did it all crooked, but there you go. 5.6. Actually, would you say? Oh, sure. So one thing that's really important to note, though, is that it's the sides that are split proportionally. It's not the parallel parts. So if I did something like that, let me add a, let me draw you a new one. So these are parallel, and let's say this time I did something like you're 5, you're 3, you're 2, and you're X. This is not side splitter. 5 over 2 would be equal to this side over this, but that's not what I have here. So what do you do with this? You can solve it, but you'd have to use the whole triangles. So for example, if I did 3 over 5, what would you have to do on the other side? X is right. X over 7. Because you'd have to do the whole side. This is not side splitter. And a lot of kids always try and force this to be. Side splitter only works on the sides, right? It splits the sides, not the parallel line. So if you have something like this, you're going to have to use the entire side. So if I do right-hand side to the whole bottom, I have to do the same thing for the big triangle. Right-hand side to the whole bottom. So that would be my proportion to solve for something like that. Okay, so just keep that in mind. Side splitter only works on the sides. Make your tree, start at the star, work your way down. You can't go sideways. That's the garland. All right, so there is that piece. The next one, I mean, this is basically the same thing as side splitter, but it's just 3 or more parallel lines. So check this out. Draw yourself any 3 parallel lines. And in fact, I encourage you to put 2 of them kind of close together. Oh my gosh, with this lead today. And then make the third one kind of further away. So they are all 3 parallel to each other. All right, so this one is saying if 3 or more parallel lines intersect transversals, then the parallel lines, divide the transversals. Again, the transversals proportionally. So they don't divide the parallel lines transversally, just like with the triangle. So check this out. So if you have some transversals here, let me just draw 2 like this. It's kind of like an extension of side splitter. Couldn't you imagine that these lines kept going and you made this little tree? So it's going to give me these pieces again. So let's do A over B equaling C over D. Okay, it's the pieces that you're allowed, as long as it's the sides, okay? It's the transversals that are getting split. A over B will in fact equal C over D. But you could not include the lengths of the actual parallel lines. So in fact, let me add that on there. Let's say that's length E and that's length F. So you could not say, for example, everybody tries to do this, like A over E is not going to be, oh my gosh, is not going to be equal to B over F, for example. You can't do stuff like that. Okay, and oh, the last one there's a sound effect that goes with this one. You ready? Let's read it and see. You should guess the sound effect. That'll be fun. Anyway, so it's the angle bisector theorem. Let's see what this says. If a ray bisects an angle of a triangle, then it divides the opposite side into segments that are proportional to the adjacent sides. What? Don't worry, I got a way to make this nice and easy. Let's start with an angle bisector. Draw yourself a triangle. I would do an obtuse triangle, just to make your life easier. Oh, thank you. Okay, and I've got lighting issues again today. All right, so draw yourself an obtuse triangle, and we're gonna bisect our obtuse angle. So draw yourself about the best angle bisector that you can. Mark that congruent, so you know, in fact, you have created an angle bisector. All right, now the words are super confusing, right? And let me just label this triangle. Let's call this triangle ABC. And we now have sides. Let's say this one's X. Let's call this one Z. This one is Y, this one is W. It doesn't really matter what they are, but I have these 4 pieces now. So here is what this is saying. If you have an angle bisector, the pieces are going to be set up in a proportion, and the easiest way to do it, instead of trying to dissect what these words mean, watch this. Take the angle that's being bisected and point it towards you or away from you, it doesn't matter, but I like to point it towards me. And then I literally just, guess what the noise is? You're just gonna go like that. What noise do you? All right, I'll tell you. You go boop. That's it. You just go boop. And you literally just have this piece over this piece equals this piece over this piece. That's it. X over Y will equal Z over W. Set it towards you and you go boop. Boop. Try it. Boop. That's it. Boop. I guess you could make your own version, but that's all. Boop. So let me give you an example of something like this. So say we did something like this. Let's say here was my angle bisector. And then I gave you numbers like, I don't know, 2, 3, X, 5. If you are trying to solve this for X and trying to figure out, well, what's the right proportion? What over what equals what over what? I'm telling you. Either have the angle that's being split pointed right at you or right away from you. So in this case, it's going right away from me. And then I just, boop. That's it. So now you know it's just 2 over 3 equals 5 over X. Boop. So much easier. Boop. When you are taking your quiz or test, feel free to boop. That's it. Cross multiply, 2x, 15, 7.5 in this case. Oh no, really is equal. That's all. Just make sure that before you boop it, you got to have the angle like pointing right at you or directly away from you. So literally turn your paper if you need to. So if I had another one, I'll just show you one more real quick. If I had something like this, and I don't know, let's say this is the one that's being bisected. And I had, I'll just make up numbers, 8, 4, 3, I don't know what that one is. If I'm going to do that, what's your proportion going to be? Yes, so I would turn it to myself a little bit, and then you, so yes, if you could mentally turn it to yourself, but you could physically take your paper and move it around, right? And you just, that's it. 4 over 8 equals 3 over X. You see? That's not so bad. Is it so bad? Ah. And then you can solve accordingly. All right, what do we think? How do we feel? Are we okay? Everything's all right? Okay, so let me stop the film for you.